Back to the Biology Bunker with Professor Carafit. Here we are with Population Ecology, Part 2. So, a few things we'll do. Talk about exponential and logistic growth patterns. You're going to be able to calculate population growth using logistic and exponential growth patterns and give examples of these in nature. Okay, so we talked a bit about demographics and we talked about curves in terms of lifespan curves that we talked about, type 1, 2, and 3. But we also need to take into account then how long organisms tend to live in the population and how many babies they tend to have each year that they're alive. And that will affect how much a population can increase during a certain period of time. Okay? And that's where we get into population growth, a study of growth of a population. So let's say we have a bacterium that can reproduce by fission every 20 minutes. So binary fission, new bacterium. Then in 20 minutes, 4 bacterium. Then in 20 minutes, 8 bacterium. And then in 20 minutes, 16. Okay? So that happens over and over and over and over again. If that were the case, if bacteria reproduced that fast and they had unlimited resources, meaning they could live everywhere and have food to eat, that bacterium that started with one bacterium 20 minutes ago, now there's 2, in 1.5 days you would have enough to cover the earth in a 30 centimeter deep layer. Okay, that's unbelievable, right? But it's true. You would have earth covered in bacteria, 30 centimeters deep. Now that is called exponential growth, where you go from 2 to 4 to 8 to 16, so on and so forth. Every time they reproduce, you get an increase of the same amount, essentially, a doubling, if you will. Now, Darwin estimated that even elephants could reach a population of 19 million in 750 years if they experienced exponential growth. Now, is that possible? Probably not. Why? Because elephants need very specific habitats, and they need room, and they need food, and there's just not enough resources to make that a reality. But any organism can experience this kind of growth at least for a while. Okay, so when we model population growth, there are a couple of variables. One is N, capital N. That's population size. We talked about that in the last video. Another one is a little letter R. Whoop, little letter R. Can't even say that. Little letter R. That's the per capita rate of increase. So I have an example here. If a population of 1,000 has an increase of 100 individuals per year, then the individual rate of increase would be 0.1. So what that's telling you is for every member of the population, how many are born in a year. Okay, that's what that tells you. So how did I calculate that? I took 100 over 1,000. That's how that was calculated. So the per capita rate of increase for every individual that there is now, how many new individuals will there be in a year? Okay. And I have a question here. What if R equals 0? If R equals 0, that means the population is not growing and it's staying steady. That means the births equal the deaths. Okay. So per capita rate of increase could be a negative number if a population's dropping instead of increasing. So if R was 0, that would mean no new births per year. And you can calculate that here. You can see on this little diagram, if you have change in population over change in time, that's the same as the change in R, or I should say in R times the population. That you see R and then that little delta T, that means the rate of per capita increase in a certain amount of time times the population size. So you can calculate how much will this population grow in a year? How many new individuals will there be in a year if this is the rate of increase? Okay, now in exponential growth, this occurs under idealized conditions. Food is abundant. Individuals have space. Everyone's healthy. Everyone's operating at 100%. That is rare in reality, right? But what happens is a population will then increase in size by a constant proportion every instant of time. Okay, so they're always increasing in time. We can see this at least at the time of this recording in the coronavirus outbreak. it's experiencing at least something close. Now, once again, a lot of populations aren't going to match a model population that we use for an example here. They might not be as steep of an increase or whatever, but a lot of populations show some variation, but we can see exponential growth in a number of places, including right now the spread of the coronavirus. Ideal conditions, they're spreading easily from person to. So let's do an example of this, and you're going to want to get out a calculator and play around with this, okay, or an Excel sheet, however you want to do it. But I want to show you how this works, and I want you to be able to calculate it because I'm going to put a question or 2 or 3 on the final. N is population size, okay? R is per capita rate of increase. We've talked about that. A population contains 10 unicorns and an unlimited habitat, so they have all the stuff they need. The unicorns have the potential to double their population every year. So R equals 1 in that case. How do we know that? R is 1. So that means for every individual now, there will be a baby made by the end of the year. Okay? So for everyone now, there's another one by the end of the year. So R is 1. Everyone adds another one. Okay? That's R of 1. Show how this population would grow in a 15-year period. So what if that were a question? How would that population grow in a 15-year period? So for example, in year 1, there are 10 unicorns, right? We start with 10. In year 2, how many would there be? Let's just start with that simple question. In year 2, how many unicorns would we have? So look at the formula here. Here's how you would calculate that. You would take R, the per capita rate of increase, times the population size, and you would add that to the population size. So 1 times 10 is 10, plus 10 is 20. So in year 2, we have 20 unicorns. Okay? How many in the next year? Well, you take 1 times 20 plus 20, and you would find out how many there would be in the next year, right? And you can keep doing that out to 15 years. And let's look at what this looks like. So here's year population 1. Year 1, we have 10. Year 2, we have 20. You can calculate this out. And I want you to try it. Try it out to like 5. Pause the video, calculate out to 5. You don't have to go all the way to 15. Just see how it works because you need to be able to do this. Okay. Here are the numbers all filled out. Notice we started with 10, and in 15 years, look at the numbers. Okay, we have a huge increase in the number. This is what it looks like on a graph. This is what exponential growth looks like on a graph. Okay, down here, this is called the lag phase. Things start, there's 10, then there's 20, then there's 40, but then eventually the curve arcs upward quite drastically. Okay, this is called a J-shaped curve because it more or less resembles kind of a weird letter J, right? A J-shaped curve is produced by exponential growth. Have a look at some of the figures showing the coronavirus outbreak, at least in the beginning of April when I'm recording this. J-shaped curve. Here is the coronavirus outbreaks in Arkansas up to a few days ago. It's not perfect. Remember, it's not perfectly J-shaped. Lucky for us, right? It starts off like a J and it increases, and right now it's kind of like this. What we want to avoid is it going like that, right? Spiking up. That's why we're doing social distancing right now, to avoid that arc going up too quickly and overwhelming our healthcare system. Okay, so that is exponential growth. When I come back on the next video, we're going to talk about logistic growth, which is maybe a little more realistic in natural situations.